Yeah, welcome. So we'll continue from what we have left in the last lecture. So in the last lecture we have discussed that a tree can be represented using list representation, something like this. But the problem with this representation is if you want to perform any operation like finding the degree of a node, finding the degree of a tree, or or what is the child of which node, or who is the parent of what, all these things is quite complex in this representation. So the ideal representation would be linked list. But the problem with linked list is you won't know like uh, each node should have how many pointers. So there is a question like each node should have how many pointers. Okay, the answer for this question is actually the node with the maximum degree will be the degree of the tree. Okay, the node with the maximum degree will be the degree of the tree. So it is enough that if each node has that many pointers. Okay. If maximum, I mean, if the degree of the tree is n, it means that there is some node with a degree n. Okay. If the degree of the tree is tree, if the degree of the tree is n means it means there is some node with a degree n, and that is the maximum degree of any node. Okay, so then it is enough to create a node with with data part and n pointers. Okay, this n can be anything, it can be 1 2 or 3 or 5 or 10, whatever it may be, right? Okay, so with this representation you can represent a tree, right? But here also again, if you see, most of the pointers will be wasted. We will not be using all the pointers, because which node will use n pointers? Only the node with the highest degree, only that will use all the n pointers. Other nodes may not use all the n pointers, they may use one pointer or two pointer or three or whatever it may be. Okay, other pointers which if a node has less than n degree, then the rest of the pointer will be null, they will not be pointing to anywhere. Okay, so is there any other way? Is there any other way to improve the efficiency? In the sense, there is one way. Okay, so actually any node, actually any tree, and any tree with any degree, any tree with any degree can be represented with just two pointers, right? Any tree and any of the nodes can have any number of childs, but still it can be just represented using two pointers. Okay, so we need just a node to hold one data part. We just need a node to hold the data part, and one pointer to the left child and another pointer to the right sibling. Okay, so with this two pointers, one pointer to the left child and another pointer to the right sibling, with these two pointers any tree can be represented. Okay, right? Let us see how that can be done, right? The tree can have any degree, the degree may be 50 or 100, even such a tree can be represented with with just this node format, with a node having, so this is a node data structure, with a node data structure which contains a place for the data part and a pointer to a left child and a pointer to a right sibling. Okay, let us see how it can be done for this particular tree, right? So if you take this particular tree, here the root node is node A. Okay, so you recollect what is our data structure. The data structure will have one data part, that is each node will have one data part, okay, and two pointers. Each node will have one data part and two pointers. What are the two pointers? One is to a left child, one is to a left child, another one is the right sibling. Okay, right sibling. Left child I'm representing as LC and right child as RS. Okay, so now you see what is the leftmost child of A. Leftmost child of A is B. Okay, so B will keep here. So node A has two pointers. What are they? Left child and right sibling. Okay, so node A's left child is now, node A's left, that left child pointer is now pointing to node B. its right sibling is not pointing anywhere, it is pointing to null. Okay, I'm not representing that, it is pointing to null. Okay, fine. And so the first child of node A is represented here, which is B. Okay, other child, what is the immediate next child of A? C is the next child of A. That will be represented as a right sibling of B. That will be represented as a right sibling of B. Okay, so now if you see A's left child is B, there is no right sibling. B's right sibling is C. B's right sibling is C. Okay, sorry for the interruption in the middle. So actually we are discussing like how to convert a tree to a left child right sibling format. Okay, that is any tree can be just represented, any tree can be just represented with two pointers. Okay, any tree can be just represented with two pointers. Of course there will be data part. Okay, and it is just enough to have two pointers. The first pointer is called as left child pointer, and the next pointer is called as right sibling pointer. Okay, so left child I'm calling as LC and right sibling I'm calling as RS. So if you take the node A, okay, so if you take the node A, so any node will have two pointers, left child and right sibling, and one data part. Okay, its left child will be B. Okay, its left child will be B, and whatever the node A's first child, that will become its left child. Okay, and the other child, the next immediate child of node A, which is C, that will become the right sibling of node B. That will become the right sibling of node B. Okay, the next child of node A, that is D, that will become the right sibling of node D. Node D, right? Okay, similarly this process will continue. For B, if you take, there are two childs. The first child is E, so E will become the left child of B. E will become the left, B has two pointers, right? Left child and right sibling. So its left child is E, its right sibling is already C. Okay, and B has another child, that is F. Now F will become E's right sibling. Okay, similarly C, if you see, there is only one child, so G will become C's left child. Okay, and there is no right for G, the right sibling will be null. Okay, if you take D, the first child of D is H, so H will become D's left child, H will become D's left child, and the next child is I, so I will become H's right sibling. I will become H's right sibling. Okay, I will become H's right sibling, and the next child is J, so J will become I's right sibling. Okay, so J will become I's right sibling, right? J will become I's right sibling. Okay, so on and so forth. Finally, if you see E will become, so I mean the E's child is K, so K will be E's left child. Okay, E has another child, that is L, so that will be K's right sibling. Okay, F does not have any child, so its left child and right sibling will be null. G does not have any child, so its left child and right sibling will be null. H has one child, which is M, so M will become H's left child. Okay, M will become H left child. Okay. And there is no, I mean, already there is a right sibling for H, that is I. There is no child for I and J. Okay. So now you can see this particular tree, okay, with the degree of 3. The degree of this tree is 3. Okay. This tree we have just represented with a node, with every node with only 2 pointers. Okay. A left child and a right sibling. So not only this tree, any tree can be represented just with these 2 pointers. I mean, any tree can be represented with nodes with these 2 pointers, left child and right sibling pointer. Fine. Okay. So this is the diagram which we got, which we form, I mean, which we got by converting that tree using left child right sibling style. Okay. So now we'll go to next level. What is the next level? This tree can be slightly modified. What modification? That is, every right sibling should be rotated clockwise by 45 degree. Okay. All the right siblings, if a particular node is a right sibling of some other node, then write it by, if a particular node is a right sibling of some other node, then rotate it by clockwise 45 degree. Okay. Right. So this is what we are going to do. So what you have to check, you take every node and check whether this node is a right sibling for some node. If this particular node is a right sibling for some node, okay, is it a right sibling for some nodes? Sn is some node. Okay. If it is yes, then what should we do? In the sense, rotate that node clockwise. Okay, rotate that node clockwise by 45 degree. Okay. So this is what we are supposed to do now. Rotate that node clockwise by 45 degree. Okay. So you have to check each and every node whether is this node is a right sibling for some node or not. Okay. Let us start with this particular node J. So is J is a right sibling for some node? Yes. Which node? J is the right sibling for I. So rotate J by clockwise 45 degree. So when you rotate J by clockwise 45 degree, from here it will come to here. Okay, from here it will come here. So if it comes here, what it will become? It will become the right child of I. Okay, it will become the right child of I. So no more, it will become the right child of I. So no more J is here, rather J is here. Okay, right. Okay. Next you see I. Is I is a right sibling of someone? Yes, I is the right sibling of H. So rotate it by clockwise. If you rotate this I by clockwise, what will if you rotate I by clockwise 45 degree, what will happen? I will come here from here. Similarly, M will also go here. Okay, M will go here. Okay, so actually what will happen? This tree will get transformed something like this. So first M will be rotated. So M will come here. M will become already M is the left child. Okay, but still M will come here. M will become the left child of H. Okay, and I will come here. Okay, and I will come here. I will become the right child of H. Okay, and J is the right child of, already J is the right child of H. Okay, it will get transformed like this, right? It will get transformed like this. Okay, so J is not here. Okay, and no more I is here. Okay, and right. So this transformation is done. Okay, now you see H. Is H is a right sibling of someone? No, H is not right sibling of anybody. Okay, what about D? Is D is a right sibling of someone? Yes, D is a right sibling of C. So when you rotate D, what will happen? When you rotate D, D will come here. D will become the right child of C. Okay, so no more D will be there. D will come somewhere here, okay. D will be here, okay, and D's left child is H. D's left child is H, okay, and C's right child will be G. Sorry, C's right child is D. D's left child is H. C's left child is G, okay, right. Previously also G is C's left child only, okay, but as there is only one child, it is represented in straight way. Now we are representing here, okay, and no more D is here. D is not right sibling. D has become the right child of C, okay, right, fine. Now you see, is C is the right sibling of someone? Yes, C is the right sibling of C is the right sibling of B, okay. Then what will happen? C will come here. So this entire thing will be rotated, okay. As there is no as there is no space, I am not drawing this. So this entire sketch will be rotated clockwise by 45 degree, and C will become the right child of B, okay. Then check F. F is the right sibling of someone? Yes, F is the right sibling of E. So rotate it by 45 degree, so F will come here. So no more F is here, okay. Then check L. L is the right sibling of someone? Yes, L is the right sibling of K. Then rotate L by 45 degrees, so L will come here, okay, right. So this also you should understand, this will come here. Is K is the right sibling of someone? No. Is E is the right sibling of something? No. Is B is the right sibling of something? No. Is A is the right sibling of something? No, right. So as a result, when you do these rotations, you will get a tree something like this, okay. You will get a tree something like this. So this tree is called as left child right child tree representation. So this representation of tree is called as left child right child tree representation, okay. Whereas this previous one is left child right sibling representation, okay. So this one is left child right sibling representation, whereas this one is left child right child tree representation, okay. So if you want to, so the takeaway point is, any given tree can be converted to just with 2 pointers. Any given tree can be represented by a node with just 2 pointers. For that, what you have to do is, first you have to transform the tree into left child right sibling format, okay, and then from left child right sibling format representation, you can again transform it to left child right child representation format, okay, right, okay. So now this tree is also called as a binary tree. Now this tree is also called as a binary tree. Why we call it as a binary tree? So the term binary represents 2. The term binary represents, the meaning of the term binary is what? 2. Binary means 2, okay. So why we call it as a binary tree? Because each node can have at most 2 children. Each node can have at most 2 children, okay. That is, if you take a typical node, it can have either 0 children or one child or two children, okay. Okay, no node can have more than 2 children, okay. Such a tree is called as a binary tree. A binary tree is a tree where each node can have at most 2 children or maximum 2 children, okay. So let us see, if you take A has how many children? Only one child. So the degree of A, number of children is nothing but the degree of the node. Degree of A is 1. B has how many children? 2. E has how many children? 2. C has how many children? 2. K has how many children? 1. F has how many children? 0. G has how many children? 0. D has how many children? 1. H has how many children? 2. I has how many children? 1. J has how many children? 0. M has how many children? 0. L has how many children? 0. Okay. So this tree, if you see, what is the degree of this tree? Degree of this tree is 2, because you cannot have more than 2 child at all. Okay. So this type of tree is called as a binary tree. A binary tree is one where a particular node, where any given node can have only at most 2 children or maximum 2 children. Okay, such a tree is called as a binary tree, right? So we will be heavily discussing on binary trees. Okay, So from as till this point, what we understand in the sense, any given tree can be represented as a binary tree. Okay, so now our concentration or focus will be only on binary tree. Okay, so if you recall the first lecture, what we discussed, tree is used to maintain hierarchical data structure. So hierarchical means for a node there can be any number of children, but now we understood that a tree can be any complex in nature, but still it can be finally converted to a binary tree by converting from what you call by representing the tree in left child and right sibling format, and then again transforming from left child right sibling format to left child right child format. Any complex tree can be finally converted to a binary tree, right? Okay, so that is the takeaway point here. Fine. And okay, so this is the abstract data type of binary tree. So hereafter what we will be discussing, it will be more on binary trees. Okay, so the abstract data type for binary tree is represented something like this. Okay, so we are defining a structure which is binary tree. It is abbreviated as bin tree, bind tree. Okay, and it's a finite set of nodes. It's a finite set of nodes. A tree is what? It's a collection of nodes, and each of the node can be either empty. Okay, empty means there is nothing. Okay, or consisting of a root node, left binary tree and a right binary tree. Okay, that is, empty means there is no tree at all, or it may have a root node and a left binary tree and a right binary tree. Okay, so what does it mean? If you see this particular, this is the root node of this tree. Okay, this entire thing is also a tree. This is the left subtree of A. This is the left subtree of A. There is no right subtree of A. Okay, so that is what that statement says. So there can be a root node and a left binary tree and a right binary tree. Okay, the left subtree is also a binary tree, right? And what are the functions we perform? What are the functions that can be performed on a binary tree? For all BT, BT1, BT2, these are, you can call it as objects of binary tree. BT, BT1, BT2, they belongs to binary tree. If there is an item which belongs to element, then what you can do, you can create a binary tree. First thing is creating a binary tree. So what are the functions that can be performed on a binary tree is, first is creating an empty binary tree. Creating an empty binary tree. Okay, so there will be a function create which is used to create an empty binary tree. And then you can have a function is empty of BT, some binary tree object, to check whether the binary tree is empty or not. If the binary tree is empty, then it will return true, otherwise it will return false. Okay, so if there is at least a root node, then it is not an empty tree. Okay, if there is no root node, then it is an empty tree. Okay, right? So like how in linked list we maintained a pointer, similarly here also you should maintain a pointer called root. You should maintain a pointer called root, and the root will always point to the root node. Okay, the root pointer will always point to the root node. So initially when there is no nodes, root will be pointing to null. If root is pointing to null, then it means that it is an empty tree. Okay, if the root here root is a pointer. Okay, if the pointer root is pointing to null, then you can say that this tree is an empty tree. Okay, so to check whether the tree is empty or not, for that we use the function is empty. Next, make binary tree which takes three arguments, BT1, item and BT2. So this will what it will do in the sense, it will create a binary tree. It will create a binary tree with a node as the root node, and the root node's data part will be item. The root node's data part will be item. Okay, and its left subtree will be BT1, and its left subtree will be BT1. Its left subtree will be BT1, and the right subtree will be BT2. Its left subtree will be BT1 and the right subtree will be BT2. So like that it will create a tree and it will return that. Okay, so it will return a binary tree whose left subtree is a BT1 and right subtree is a BT2, and root node contains the data item. Okay, then left child of BT. So BT is something like a pointer. Okay, you can BT probably it will be pointing to the root node. Okay, so it will uh, or it will point to anything which you want to check. Okay, so this will check whether the left whether for a particular node, if BT is pointing to a node, whether for this particular node is there is a left child or not. Okay, if there is no left child, it will return error. If there is a left child, it will return a pointer to the left subtree. Left child is nothing but the left subtree. Even if there is only one node, that is also a subtree. You can call it as a subtree. Okay, right. Similarly, data of BT, it will check whether data of BT is empty or not. If it is empty, it will return error. Otherwise, it will return the data of that particular node. So BT points to the node. BT points to any node. Okay. Similarly, next function OR child, right child of BT, it checks whether for this particular node is there is a right child or not. If there is no right child, it will return error. Otherwise, it will return the right subtree, that is the pointer to the right subtree of that particular node, it will return. So these are some of the operations, typical operations that you can perform on a binary tree, right? Okay. So here are some sample trees. So if you see this tree, this type of tree is called as skewed trees. So this is an example for a skewed binary tree. This is also a skewed binary tree because if you see this type of tree, every node is having only a left child. A is having a left child, and B is having a left child, C is having a left child, D is having a left child. So this is skewed in the towards the left. Okay, whereas this tree, if you see, it is skewed towards right. Okay, this type of tree is called as skewed binary tree. Okay, so there are different types of binary trees, right? And this binary tree is called as a complete binary tree. Why we call it as a complete binary tree, and what is a complete binary tree? In the sense, okay, if you see, A has two child B and C. Okay, B has two childs D and C has two child F and G, D has two childs H and I. F and G don't have any child. Okay, so everything, all the nodes are filled in order. All the nodes are filled in order. So that is, after A you have B and C, after C you have D and E, after E you have F and G, then you have H and I. That is not in the alphabetic order. I mean, there is a left child for A, and then there is a right child for A, then there is a left child for B and a right child for B, then there is a left child for C, then there is a right child for C, then there is a left child for D, and then there is a right child for D. So for whatever the nodes, there are child nodes. There are child node for, there is a left child and also a right child. So such a tree is called as a complete binary tree. Okay, for example, say for G, now I am adding on left child Z. Now if this Z is added, then this is not a complete binary tree. Okay, if this Z is added, then this tree will not be called as a complete binary tree. Why? Because after E, if you follow the order, after I, if you follow the order, there should be a left child for E. Okay, then there should be a right child for E, then there should be a left child for F, and then there should be a right child for F, and then Z should come. Okay, otherwise you cannot call it as a complete binary tree. Okay, otherwise you cannot call it as a complete binary tree. For example, if after E here, if after I here J is added as a left child of E, then still it is a complete binary tree. Okay, because still the order is followed, right? Okay, so none of the node in the order should be skipped. If that is the state of the binary tree, then such a binary tree will be called as a complete binary tree. Okay, and if a binary tree has depth of k, what is depth? Depth is nothing but level. If you take this binary tree, what is its level? This is level 1. Okay, this is level 2, this is level 3, this is level 4. Okay, level is otherwise called as depth. Okay, so it is either called as level or it is called as depth. You can call it as either level or you can call it as depth. Okay, So for this particular tree, the level is 4 and also the depth is 4. So if a binary tree has a depth k, then maximum it can have how many nodes? Then maximum it can have 2 to the power k minus 1 nodes. Okay, right? If the binary tree has a depth k, then maximum how many nodes it can have? Then maximum it can have 2 to the power k minus 1 nodes it can have. Okay, so here if you see, this is not a so maximum this tree can have how many nodes? Maximum it can have another 2 nodes for E, and it can have another 2 nodes. F it can have another 2 nodes. Okay, and G it can have another 2 nodes. Okay, this is the maximum number of nodes you can have for this tree with level 4. Okay, so this is level 4, level 4, right? With level 4, this is the maximum number of nodes. So what is the formula? If the number of level is k, then the maximum number of nodes is 2 to the power k minus 1. Okay, so what is 2 to the power 4? What is 2 to the power 4? 2 to the power 4 is 16. Okay, so 2 2s are 4, 2s are 8, 16. Okay, 16 minus 1 is what? 15. Okay, so 16 minus 1 is 15. So it can have maximum 15 nodes, right? So that is the point. If the level of a binary tree or the depth of the binary tree is equal to k, then it can have maximum 2 to the power k minus 1 nodes. Okay, so you can add these 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Okay, right? Fine. Okay, and another point is the maximum number of nodes on the level I of a binary tree will be 2 to the power I minus 1. Again, it's same, it's understandable, right? K is nothing but the depth of the binary tree. The maximum number of nodes on level I will be 2 to the power I minus 1. Okay, 2 to the power I minus 1, right? So if you take this particular tree again, what is the maximum number of nodes at first level? 2 to the power I minus 1. The first level I is 1. Okay, 2 to the power 1 minus 1, that is 2 minus 1 is 1. What is the maximum number of nodes at level 2? Again 2 to the power I minus 1. Okay, this is what? 2 to the power 2. Okay, 2 to the power 2 minus 1 is 2 to the power 2. 2 to the power 2 minus 1. Okay, so this is level 2. Okay, 4 minus 1 is sorry, it is just 2 to the power, it is just 2 to the power I, right? 2 to the power of I minus 1. Yes. Okay, so on the power it is I minus 1. Okay, so it is 1 minus 1, so 2 to the power 0 is 1. Okay, so again here also 2 to the power 2 minus 1. Okay, so what is that? 2 minus 1 is 2. Okay, so now we are calculating number of nodes in ith level. In first level there is only one node. In second level there is only 2 nodes. Okay, let us calculate for third and fourth level. So in third level, maximum how many nodes you can have? So 2 to the power 3 minus 1. Okay, what is 3 minus 1? 2. So 2 to the power 2 is what? 4. Okay, and how many nodes here? We have 4 nodes. We have 4 nodes here. Okay, so if you look for the next level, here you can add 2 more nodes. Yeah, here you can add 2 more nodes, and here also you can add 2 more nodes. Okay, so now if you see, this is level 4. So level 4 is 2 to the power 4 minus 1. What is 4 minus 1? Which is 3. So it is 2 to the power 3. So 2 to the power 3 is what? 2 2s are 4, 4 2s are 8. So you can see how many nodes here? 1 2 3 4 5 6 7 8. Okay, so the point is the number of nodes at a given level. Okay, the number of nodes at the ith level is 2 to the power I minus 1, right? Will be I minus 1. Okay, 2 to the power I minus 1. And if a tree's depth is k, then the number of nodes, then the maximum number of nodes in the tree can be 2 to the power k minus 1. Okay. Right? So this is also maximum number of nodes in the ith level. The maximum number of nodes in the ith level can be 2 to the power I minus 1. Okay. And if a tree is of depth k, then the maximum number of nodes in that tree can be 2 to the power k minus 1. Fine. Okay. Now let us try to understand what is meant by a full binary tree. Okay. A full binary tree is something if the depth of the tree is k, if the depth of the tree is k, if the depth of the binary tree is k, then it should have 2 to the power k minus 1 nodes. Okay. Such a binary tree is called as a full binary tree. Okay. Right. So what is a full binary tree? If the depth of a binary tree is k, then it should have 2 to the power k minus 1 nodes. If that condition is satisfied, then such a binary tree is called as a full binary tree. So if you see this right side tree, this is a full binary tree because it has how many nodes? It has what is the depth? What is the depth of this tree? 4, and it has how many nodes? 2 to the power 4 minus 1 nodes. That is, it has 15 nodes. Okay. So such a binary tree is called as a full binary tree. And what is a complete binary tree? We have already discussed, but it is defined here. If a binary tree has n nodes, and the depth k, and with the depth k, then we call that binary tree as complete if and only if. This represents if and only if. Okay. If and only if its nodes corresponds to the nodes numbered from 1 to n. Okay. If and only if its nodes correspond to the numbers numbered from 1 to n in the full binary tree. Okay, of depth k. Right. Okay. So that means that if you number these nodes, then this is 1, 2, 3, this is 4, okay, this is 5, this is 6, this is 7, this is 8, this is 9, okay. But so this is a complete binary tree because it is in that order. Okay, the nodes corresponds to the nodes numbered from 1 to n in the full binary tree. Okay, so if you number in a full binary tree, how will you number these nodes? If it is a full binary tree, then here also you should have nodes. Okay, F also you should have nodes. Here also you should have nodes. Okay, then how will you number? This will be 9, this will be 10, this will be 11, this will be 12. Okay, this will be 13, this will be 14. Okay, this will be 15. Right, in a full binary tree. Right. Okay. In this case, this is not there, but this is a complete binary tree. But let us assume that in this tree I am adding a node here. Okay, if I add a node here, then this will not be a complete tree because these nodes are not there. And I am directly adding a tree node here. And what will be its number as of this tree? After 9, I have to number this as 10. After 9, I have to number this as 10. But if it is a full binary tree, what would be its number? 15. So is this number is matching? It's not matching. Okay, that is what the definition says. So if the number of a binary tree, if the numbering of the node of a given binary tree does not matches with the numbering of the respective full binary tree, then such a binary tree cannot be called as a complete binary tree. Okay, if the numbering of a particular node of a given binary tree matches with the numbering of if the numbering of a node of a given binary tree matches with the numbering of the particular node in the full binary tree, then you can say that that tree is a complete binary tree. Right. Okay, so the point is, in complete binary tree the nodes should be added in order. Okay, if it is not following that order, then you cannot call it as a complete binary tree. Right. Fine. Okay, so here there are some other details. So if there is a complete binary tree with n nodes, then its depth will be equal to log n plus 1. Okay, so this is something like a formula you can remember. If what is a complete binary tree, you know, in a complete binary tree the nodes should be ordered in number, and and the numbering should be matched, and the number of any given node should match with the respective number of the full binary tree. Only if it is matches, we will call it as a complete binary tree. Otherwise, we won't call it as a complete binary tree. Okay. If a complete binary tree has n nodes, then its depth will be log n plus 1. Okay. Then its depth will be log n plus 1. Okay. For any given node, right? Okay. For any given node where for any node with index I, where I is between 1 and n. Okay. Right. Now, see, this is separate. Okay. For so this first point is separate, second point is separate. Okay. Let us not combine that. For any binary tree with n nodes, it will have a depth of log n plus 1. Okay. Full stop. Right. Then consider a particular node I. Let us consider any node with index I. Okay, where I is between 1 to n. Okay, n is the number of nodes, so I can be either it may be with the first node, second node, third node, or up to nth node. Okay, then we have this information. Okay, so I represents some node. Okay, so what will be the parent of I? If I is some number. Okay, if I is some number which represents the particular node number, then the parent of I will be I by 2. Parent of I will be I by 2 if I is not equal to 1. Okay, if I is 1, then it is the root node. If I is 1, then it is a root node. Okay, for example, if you see this particular tree, this is node 1, this is node 2, this is 3, this is 4, this is 5, this is 6, this is 7. Okay, let us take this 6. Okay, let us take I as 6, which represents this particular node, 6th node. Okay, so what is its parent? So parent of 6 is, so parent of I is nothing but I of 2, I by 2. So parent of 6 is nothing but 6 by 2. What is 6 by 2? Which is nothing but 3. So parent of 2 is nothing but node 3. So this is the case if I not equal to 1. This is the case if I not equal to 1. I is here not equal to 1. If I is equal to 1, then I is the root node. Okay, the first case alone I is the root. If I is equal to 1, then that is the root node. That will not have any parent. Okay, and for any node I, okay, the left child of I will be equal to 2i. Okay, left child of I will be equal to 2i if 2i is less than or equal to n. Okay, if 2i is less than or equal to n. If 2i is greater than n, then I is the leaf node. If 2i is greater than n, then I is a leaf node. Okay, again if you take this particular node 6, okay, what is its left child? So as of the formula it is 2i. So 2 into 6, then this should be 12. 2 into 6, then this should be 12. Okay, so let us number 8, 9, 10, 11 and 12. Okay, and also you should check whether this number is less than or equal to n. In our case n is 15, it is less than or equal to n, so its left child will be 12. Okay, if this number is greater than n, then there is no left child. This f is the leaf node. Okay, and what will be the right child of I? The right child of I will be 2i plus 1. It will be 2i plus 1 if 2i plus 1 is less than or equal to n. Otherwise right child is the, otherwise I is the leaf node. Okay, otherwise I is a leaf node. Okay, or you can say yeah, otherwise I is a leaf node, right? Okay, fine. So so the point is, so again you take node 6. So node 6, 2i plus 1 is what? I is 6. Okay, 2, 6, 2 are 12 plus 1, 13. So 13 is its right child. Okay, if 13 is less than or equal to 15, then node 13 will be its right child. Suppose if it is greater than 15, then I is the leaf node. Okay, then I is the leaf node, right? Okay, so these are some of the representation. So you should be able to remember this. Parent of I is nothing but I by 2, as long as I not equal to 1. If I is 1, then it is the root node. Left child of I is nothing but 2i. Okay, as long as 2i is less than or equal to 1. Okay, if 2i is greater than 1 n, then I is the leaf node. Right child is equal to 2i plus 1 if 2i plus 1 is less than or equal to n. If 2i plus 1 is greater than n, then I may be the leaf node. Okay, right? Okay, fine. Then is there any other way to represent a tree other than linked list representation? Is there any other way to represent a tree, you may ask? Yes, you can also represent a tree by using array. Okay, but there is some drawback with that technique. uh, there is a lot of wastage of space, and also insertion and deletion will become very complex. Okay, but let us try to understand how a given tree can be represented using arrays. Okay, so let us assume this is a tree. It's a skewed binary tree. It is skewed towards left. Okay, but how can we represent using array? Okay, so what is a? The first node, root node, will come to the first location of the array. Here we assume that array starts at location 1. Okay, in C it may start with 0, but let us assume array starts with index 1. So root node comes here. Okay, is there a left child for root node? Yes, put it in the second location. Is there a right child for root node? No, so keep it empty. Okay, keep it empty. Fine. So there is no right child. Then come to the left child of root node. What is the left child of root node? B. B is already entered. Is there a left child for B? Yes. Fill up here. Is there a right child for B? No. So leave it empty. Okay. Now you have done with the left child of A. Now go to the right child of A. Is there a right child for A? There is no right child. So that is what we have mentioned here. Okay. There is no right child. There is no right child. So that means that there is no left child for this one. Actually there is no right child for A, but we have given a space for that in the memory, right? To even to know that there is no right child for A. Okay, right? I think you are following. So this location corresponds to the right child of A. As there is no right child, we have represented as dash. Okay, so this dash is nothing but the right child of A. Does this dash has a left child? Does this dash has a left child? No, because that itself is not a node, so there is no left child. Does this dash has a right child? No. Okay, so these two are for that. Okay, right? So now we have done with the left child of A and also right child of A. Now come to the left child of B. Okay, now come to the, that is C. Left child of B is C. Does C has a left child? Yes. Okay, does C has a right does C has a right child? No. Does C has a right child? No. Okay, now similarly you have to do for the right child of B. Okay, what is the right child of B? For this there is no left child, no right child, that you have to enter. Like this you have to fill up. Okay, but if you see, if you fill up like this, what happens? There are many locations which are empty. To represent that particular node does not have a left child or a right child, you have to make many empty locations, so which will create a lot of space wastage, and insertion and deletion also, it is complex with this representation. Okay, so this is the reason we are not going for this representation. So normally trees will be represented using linked list. Okay, fine. So how could we define a node? So you can define a node something like this. Okay, so actually this type of definition is allowed in C. This may look little different, but it is allowed in C. So first you don't see this statement. First see this for understanding. Okay, just ignore this first line, or I will strike it out. Okay, here what we do is type def struct node. So we are creating struct node and we are making it as a type def, because we want to make it as a user defined data type. Then we are creating a data of type integer. Okay, which is a data part, right? Then we are creating a pointer left child and a right child. These two are pointers, so we are calling it as tree pointer. But what is the tree pointer? What is a tree pointer? It's not a predefined data type, it is a user defined data type. What is tree pointer means? Tree pointer is a pointer. Okay, so this is how tree pointer is defined. Star tree pointer. Okay, it's a pointer to what? Struct node. It's a pointer to struct node type def. Okay, So type def is used to create what? User defined data type. So now you have created a user defined data type. The name of the user defined data type is what? Tree pointer. So this tree pointer can point to where? It can point to any node, any struct node. Okay. So here why it is little different in the sense, before defining the struct node you are using the struct node. Are you getting? If this is statement 1 in the program, if this is statement 2, then actually struct node is defined in statement 2, but here you are using struct node even before defining it, but that is allowed in C, okay, right? So if you feel this is not understandable for you, then don't consider this, okay? Don't leave this, take away this type definition also. Instead of this tree pointer we can say struct node store, like how we used in linked list. It is the same thing, but we are representing in a different way, right? You can say that struct node store. What does it mean? It means that left child is a pointer to another node and right child is a pointer to another node. So it is very similar to the doubly linked list. In doubly linked list also you have one data part and two pointers, previous and next. Similarly you have here left child and right child, okay, right? But actually the textbook follows this representation. This is correct. It is not that it is wrong. You see allows you to use a structure. C allows to create an user defined data type for a structure even before the structure is created, okay? So the structure struct node is not created, but before that we are creating an user defined data type for that, which is store tree pointer. That is, it is a pointer. Using this you can define data types like a pointer to the structure node, okay? So when you create the data type here, you are not using store, right? So it is not required because already you have given that, you have specified that it is a pointer, okay? So here when you say, you can just say tree pointer left child and right child, but actually now left child is a pointer and right child is also a pointer, okay? So simply putting this statement is equivalent to writing struct node store, right? So this will create a node, something of this nature, okay? The node will have a data part and it will have a pointer to a left child and a pointer to the right child, and this is its representation. There is a data part, there is a left child point, there is a pointer to left child and there is a pointer to the right child, okay? Fine. I think let us stop here. Other things we'll discuss in the next lecture. Thank you.